All right, our next speaker this afternoon is Stephen Romero-Ruiz, who's joined us from Caltech. This summer, he's been working with Stella, and he'll tell us about their project together, characterizing pulsar distances with H1 kinematics.
Thank you, Gwen, for the warm introduction, and thank you all for being here to listen to my presentation. So let's dive into a little bit of a background of this project. So what are pulsars, and why do they actually matter to us in this case? So pulsars are these fast rotating neutron stars that emit these radio waves from their poles. We can observe that as these periodic pulses, hence given that the name pulsars. Now, why do they actually matter to us? Well, the distance measurements can actually help us understand other sorts of pulsar applications, such as testing general relativity theories with these pulsar binary systems, and also developing an electron density model of the galaxy to help us study the ISM a little bit more. So there's a variety of issues with pulsars, but the two main ones is basically we have a very small sample size of pulsar distances that we have compiled. And most of them, as you can see in the figure on the right there, on the outer rims of the galaxy, they kind of have very large uncertainties and can be really poorly constrained. So how do we actually calculate the distance measurements of these pulsars? There's three main ways. The first one being through parallax, and kind of see a little schematic on the right. And this uses very long baseline interferometry, which can take months or even years to actually get a pulsar distance measurement using this method. And the next is through association, which kind of gives it away to the name. We kind of associate the pulsar with some sort of globular cluster or supernova remnant that we have a distance measurement for, and we associate that with the pulsar distance. And the next one is through H1 kinematics, which I'll dive into deeper detail in the later slides. And out of the 3,000 pulsars that we know exist in our galaxy, we only have distance measurements for around 300 of them. And as I mentioned before, what we can do with these distance measurements is basically develop an electron density model with the following equation below that was adopted in Ferlin-Weisberg from 1990. Basically, you get this distance measurement of a pulsar along a line of sight, and you can also observe its dispersion measure and extract this variable down on the bottom, seen as NE, which is basically the electron density or the mean free electron density for that pulsar along that line of sight. So you may be asking, what is this dispersion measure value? So this is basically this frequency dependent time delay where we observe these higher frequencies arriving quicker to us compared to the lower frequencies emitted by the pulsar. And that can be shown in the figure on the right there. And if we can basically get all the pulsar distances along all these different lines of sight and all these observed dispersion measures of these pulsars, we can extract this NE variable and develop an electron density model for the galaxy. And also with that electron density model for the galaxy, we can basically approximate the distance measurements of the other pulsars we don't have distances for with their observed dispersion measure. So we look primarily into H1 kinematic distances, mostly because they take a substantial fraction of the pulsar distance measurements that we have. So on the schematic on the left, you kind of see this little cartoon on the far left, which basically depicts the idea of what an H1 kinematic distance is where we have these two H1 clouds that can potentially bound the pulsar, and we can extract the distances of those H1 clouds. And those distance measurements can bound the distance measurement of the pulsar, as you see on the left here. So you may be asking, how do we actually even determine whether we even have these H1 clouds on the line of sight of the pulsar? Well, we can basically establish whether we have a lower bound H1 cloud when we look at the absorption spectra of the pulsar, and we see a deep enough absorption feature. And that means basically the H1 cloud is at least absorbing something from the pulsar. And then we can establish whether there's a upper bound H1 cloud when we look at both the emission spectra and the absorption spectra. And we notice a feature on the emission spectra without an accompanied feature on the absorption spectra. And that's mainly because the H1 cloud isn't absorbing anything from the pulsar, but it's emitting something from behind the pulsar. So once we establish these features with the H1 clouds, we can basically Doppler shift them to the reference wavelength of 21 centimeters to extract the radial velocity measurement of those H1 clouds. And once we get those radial velocity measurements of those H1 clouds, we can translate them to distance measurements using a rotation curve along that line of sight for that pulsar. And the main caveats behind this kind of method of determining these distance measurements is sometimes the radial velocities of the clouds can be, I guess, not poorly calculated, but the peculiar motion of certain spiral arms can kind of give us a false distance measurement when we're translating it using the rotation curve model, because sometimes they don't actually account for that peculiar motion. And also sometimes we can only have like one H1 cloud that we can at least establish and get only one distance measurement for one H1 cloud. So since we're looking into H1 kinematics, we got to look into the rotation curve models that actually help us translate these H1 cloud radial velocities to distance measurements. So on the left, you kind of see this rotation curve model that was adopted in from 1989 using the in the Fitch et al. Paper. And this is primarily fitted to H1, H2, and CO distance measurements. And as you can see here on the figure on the left, on the bottom left, we're plotting basically circular velocity of objects around the galaxy over a function of galactocentric radius. And you kind of see here all the data they use for this model. And as you go more on the outside of the outskirts of the galaxy, you kind of see a higher uncertainty in those measurements. And then the new model, the Reed et al. 2019 rotation curve model, is primarily fitted to around 200 Maser parallax distance measurements. And again, the plot on the bottom right is in terms of circular velocity of objects around the galaxy as a function of galactocentric radius. And you see here the black dots are laser is, but the black dots are much more constrained and don't have higher uncertainties compared to the last model. So the first step in our research project this summer was to basically understand how we actually calculate these H1 kinematic distances. And we do that by looking at this paper, Fairland Weisberg, 1990, and this was the actual last pulsar distance catalog. So we haven't actually updated these distances measurements since 1990. So here is a kind of an example of one entry for a H1 kinematic distance for one pulsar in this catalog. So you see here we're given various things such as the pulsar name, the line of sight of the pulsar, its dispersion measure, the radial velocities of the H1 clouds if they exist, and their derived distance measurements that they use when they use the Fitch et al. 1989 rotation curve model. So what we're trying to do is our first step is basically plot some sort of rotation curve model along the line of sight and use the radial velocities that they give us in the catalog and try to replicate the distance measurements that they derived. So here's just a small example of like one pulsar that we did this for, pulsar J074028. We basically plotted the Fitch et al. 1989 rotation curve model along its line of sight of the pulsar. And that can be shown as the blue line, where it's plotted over radial velocity over a function of distance from the sun. And given the H1 cloud radial velocities they give us in the catalog, we plot those horizontally and calculate the intersection with the rotation curve model, and that will give us the H1 kinematic distance. So here the green horizontal line is basically the lower bound H1 cloud radial velocity, and the red horizontal line is the upper bound H1 cloud radial velocity. So on the right, you kind of see a little histogram of the fractional differences between the distances that we derived compared to the catalog. So if we have a low fractional difference, that means we're understanding how to actually calculate these H1 kinematic distances and replicating the catalog correctly. So after we understand how to actually calculate these H1 kinematic distances, we can apply the new rotation curve model from 2019. Just a reminder, here's basically the differences between the two models. As you can see, the red is the newer one from 2019, and the blue is the older one from 1989. And we kind of go about the same process of for all 50 pulsars. We kind of just plot the rotation curve model along its line of sight. So here, kind of the same labels. We have the radial velocity over a function of distance from the sun. So here the blue is seen as the new rotation curve model from 2019, and the orange is seen as the old one from 1989. And then again, if the H1 cloud radial velocities exist, we plot them horizontally against the rotation curve model. So here the green again represents the lower bound H1 cloud radial velocity, and the red represents the upper bound H1 cloud radial velocity. And the solid circles represent the intersections between the radial velocities in the new 2019 rotation curve model, and the stars represent the intersections between the radial velocities and the old rotation curve model from 1989. So we're usually seeing a fractional difference of around 10% between our newly compiled H1 kinematic distances using the new model from 2019 and the the old catalog distances. And we're usually also seeing a trend that these distances appear closer to us than the old catalog distances. So that can be due to basically the rotation curve model, obviously, since we isolated that. But more in depth, it can be basically due to the galactic constants that were updated using this new rotation curve model. So after we compile these H1 kinematic distances, we want to apply some Bayesian inference approach to basically derive the uncertainties of these H1 kinematic distances. Since the rotation curve model can have some uncertainties in its parameters, and also some H1 kinematic distance parameters can have uncertainties as well, which can lead to these H1 kinematic distances having uncertainties on the scale of kiloparsecs. And we kind of just did a little basically resampling the rotation curve model first, and here's the model resample. We basically did an MCMC algorithm on the parameters to randomly resample them, and then we basically plotted a 2D histogram of the different kind of or like all like the rotation curve models with all these resampled parameters. So in conclusion, we basically want to create a new H1 kinematic distance catalog for these 50 pulsars that haven't been updated since 1990. And this can be used to develop a new galactic electron density model for the galaxy, which can help us study the ISM a little bit more clearly, and also determine distance measurements of other pulsars. Thank you.
Okay, very nice. Questions for Stephen?
Like, I know part of finding Pulsar is something of that time level is including what for the class. And I was wondering if any of the studies you're looking at have stable enough models to compare your H1
yeah, so my mentor she gave me a website that kind of had a database of like all like these pulsar distance measurements, and thankfully enough, most of these some of these H1 kinematic distances have actually been updated to Maser parallax distance measurements, so we can for sure actually like compare our new H1 kinematic distances and see if they actually at least constrain that sort of pulsar.
Other questions for Stephen? Anna.
Question about the Bayesian analysis. So we knew get an uncertainty on the distance measurements from this, and what are you finding to be the dominant source of uncertain, like your distance uncertainty?
Yeah, so we kind of like hit a little roadblock on that area, mainly because like the Frel and Weisberg 1990 catalog kind of like don't explain the way they derive their uncertainties. They kind of just mention a lot of references, like these very old references from like very old papers that are very hard to find. And it's kind of hard to pinpoint the exact way that they kind of get these sort of uncertainties for their distance measurements. But so I haven't actually like calculated the uncertainties of these distance measurements, but that is something we will look into in the future.
Thanks, Stephen, again.